Okay, and all of these are under practice test 4 or test 4 practice online. I'll just leave that there. But, okay, molecular geometry. Just have to add that. Okay. So I will give you the Lewis structure to look at to do this molecular shape stuff. So as we start today, let me give you, you can go ahead and write these down because you'll want them for practice. But on this first page where it says Lewis dot structure, you want to put that for the first one. I guess some of these will build. SiH4 is I'll come back to SO3 just to double check it. PF3. So write down those two, and we'll go through and build these just as a reminder on how to do Lewis structures. SO3, okay. How many valence electrons are in sulfur and oxygen? 6. So if we have this, we have 6 and 4 is 24, so we have 24 electrons. All right, and if we just start and we put S in the middle, I'll start my Lewis structure that way, which means I've already used 2, 4, 6 electrons. So I'm down to 18. Do you remember what's next? Next, I start filling in the octet on the outside atoms. This means there's already 2 around this oxygen, so I need 2 more, 2 more, 2 more. Now there's 8 around it, so I'm filling in the octets on the outside. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's all 18. I'm down to 0 electrons. There's still a problem though. What do you think the problem is? In terms of octets, this has 8, this has 8, this has 8. Now the central atom does not have 8. So what you do is you borrow, just pick one from one of these pairs and make a second bond. Now sulfur has 8 electrons around it. There's 2 electrons in each line, in each bond. So that does it. That's the Lewis structure for SO3. PF3, how many valence electrons in fluorine? 7, and there's 3 of them, so that's 21 electrons. How many for P?
For P, it's 5.
It's 5. So 21 plus 5 is 26. So I have 26 electrons. I'm going to put P in the middle, put my F's out like this. And I use 2, 4, 6 electrons, so I'm down to 20. And now I'm going to fill in these 2, 4, 6, 8, 10, 12, 14, 16, 18. So I've got 2 left. minus 18. I've got 2 electrons left. I'm going to put those in the middle when you have some left over, like that. And now everything has its octet, so that's the Lewis structure for PF3.
Is it 3 already?
Say again?
Even on the paper says 5 fluorines.
Oh, I read it wrong. PF5, okay. There is such thing as PF3, but we'll do it like the sheet does. So now how many electrons? 35 plus 5, so there's 40. Is that right? 40 electrons? Right? So now I'm just going to do this. I'm going to put 5. Um, 40 electrons, okay. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. It's minus 30, but I didn't count these yet. 2, 4, 6, 8, 10, minus 10. Okay, that's all. That's the structure for PF5. You got 3 pairs of electrons, 1 line here going to the P. I mentioned last time, but I probably only ever said it once, that starting with phosphorus and then going this way and then going all the way up, you can have more than 8 electrons around these. So starting with phosphorus and anything bigger, you can have more than 8. These are exceptions to the octet rule. Other exceptions to the octet rule is hydrogen is only ever going to have 1 bond to it. So it's only ever going to have 2 electrons around it at most. Boron is only going to have as much as 6. So those are less than 8. So for boron, it's a max of 6. For hydrogen, it's a max of 1. Let me just do BH3. So how many valence electrons for boron? 3. And then 1 each for hydrogen. So we have 6 total. If I did this, 2, 4, 6, that's it, that's BH3. And notice it doesn't have an octet around it, but you still stop there because boron can only have as much as 6 around it. And hydrogen can only have as much as 2 electrons around it. SF5Cl. We've got 35 electrons. Do it over here. 35 electrons from fluorine. We've got 7 more for chlorine, so that's 42. And how many for sulfur? This is too easy to not know how to do. You start with sulfur and you count it 1, 2, 3, 4, 5, 6. So everything in this row has 6. Everything in this row has 7. 5, 4, 3 for boron. What did I just say? 6. So we have a total of 48 electrons. Sulfur in the middle, and I'm just going to put everything around it. One of these is chlorine. 2, 4, 6, 8, 10, 12. I've used 12 already. So I've got 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 5, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. That's what we were down to, 36. We're down to 0, and that's it. And yes, sulfur has more than 8 again. So those are those structures for these. All right, number of electron domains. These aren't the best examples, but we will have some PCl3. So we'll go through all of these. Electron domains. Let me circle the domains. Here's what I'm calling electron domains. For BH4, it's those 3 things around boron. So 3 electron domains. This 2 bonds, that's 1 electron domain. 2, 3. This has 3 electron domains. 1, 2, 4, 5. 5 electron domains. This one has 6. 1, 2, 3, 4, 6. 6 for that one. All right. The geometry. Let me open this, which may be better. Downloads. And this will help too. This. You could link to this. Just because it's helpful. I'll write down all electron pair don't worry about this acronym. It stands for valence shell electron pair repulsion. But the whole idea is, if you have, say, you have that molecule. Notice there are no electron pairs around carbon. So if I was focusing us on carbon, and I'm trying to say, what is the shape around carbon? So every time we draw these types of diagrams, they're always flat in this 2-dimensional plane, but not all molecules are flat like that. So valence shell electron pair repulsion theory helps you predict what the shape is. If I was going to circle the electron domains, I would go, there's one, and there's another one. There's 2 electron domains there. And those electrons repel each other. So the valence shell electron pair repulsion is saying these over here on this side of the carbon are repelling these on this side of the carbon. And the question you ask is, how do they get as far away from each other as possible when it's just shaped in this linear way like that? And obviously, for them to get as far away from each other as possible, get this off. For them to get as far away from each other as possible, I want us to be able to see the video. Then this is the shape they'll be in. If you look at this little cheat sheet here, what some books call it electron domains, some call it electron regions. There's a phrase that I've never heard before in your lab that's calling them steric numbers. But look at that first entry on here. It says there's 2 electron regions. The way those 2 electron regions get as far away apart from each other is to do like that. And essentially that means the shape of that is linear. That's probably obvious that it's linear. Maybe not as obvious, but after I say it, maybe it's obvious. Those electron domains to get as far away from each other as possible means they're 180 degrees away from each other. The other thing to point out here is this is, of course, a straight line, and it's 180 degrees. So if you ask what the bonding angle is, the shape here is linear, and the bond angle is 180 degrees. All right, maybe that one's obvious. Let's keep going. This is, you can download this too. It's on D2L under test 2 practice. But if I said BECL and you built this Lewis structure, you would look at it and go, okay, there's 2 electron domains. 1, 2. And if those are going to get as far away apart from each other, they're going to be 180 degrees away from each other. The shape, we call that as linear. Really what we're saying is the shape around beryllium is linear, but because this is all there is to the molecule, you can't actually say the overall molecule is 180 degrees. Or you can say the overall molecule is linear. But usually, I mean, the truth is molecular shape, you have to point at one atom in the molecule and say, what is the shape around that? Because this is what we're saying, electron domain over here, electron domain over here. It's just all the examples for these all happen to have a central atom whose shape ends up defining the entire molecule. All right, just to go through these. I want, this would progress better if I have some. All right. SO2, there's the shape of SO2. If I said, where are the electron domains here, I would circle this and say 1, and I'd circle this and say 2. And actually, a pair of electrons, that counts as a third one. So you're looking at 3 electron domains here. You with me? You count a pair as 1. And you count bonds, whether there's 1, 2, or 3 in the bond, as 1. All right, so on this sheet, we're down to the next row. I'll let that sit here, but let me do, Emily, come get one of each of these. Let me just back off to BF3 again. So linear, 180 degrees, 2 electron domains. Let me do BF3 again because it's a better starting point than the one I've got over there. BF3, okay. If I gave you this as a Lewis structure, how many electron domains do you have? 3. There's 3. If you have 3 things around a central point, I said what happens when there's 2 things around a central point that repel each other. That's linear, 180 degrees. Those are all single bonds. If all 3 of those things are trying to get as far away from each other as possible, maybe you have to think about it for a second, but this is what they're going to do. They are all actually in a plane, and you know, this is 180 degrees around to here if it's a flat plane. But if I squeeze this in a little bit, that would decrease the 180 degrees, so that would get them closer to each other. But really the angle here that counts is this angle. Do you know what angle this is? 180 degrees is obvious, but since this is flat and this is like a circle, how many degrees do you think are in each one of these? 360 divided by 3, which is 120. Goodness. And that's what it says on there. So if you've got three things in a plane, the angle they have from each other is 120 degrees. So this is called trigonal planar, and the angle associated with it is 120 degrees. So trigonal, because this is essentially a triangle, all in a plane, so planar, 120 degrees. So everything down that first column, I think your lab mentions this, so I'll mention it. You look at it and you say, so for your lab, today's lab, you see electron geometry and molecular shape. Those two things are closely related. I'll say DF3, this is, that's the molecular shape, but it's its electron geometry is also trigonal planar 120 degrees. So there's really two concepts that go with this idea of shape. There's molecular shape. This one's molecular shape is trigonal planar. And then there's electron geometry. This one's electron geometry is also trigonal planar. Really, you consider this one first. So I should have put that on top. But to show the difference between electron geometry and molecular shape, let's go back to this one. I asked you before how many electron domains are here. I pointed out that's 1, that's 2, and that pair actually counts as 3. Let me draw that over here. Really a slightly better representation of this is to actually make it look like a triangle. That, that. So that's what's up there, but really a slightly better way to draw it is so it looks like a triangle. And this electron pair, let me shift them up here a little bit and just kind of make a dotted line that goes out to that pair. So still, you've got 1, 2, 3. So 3 electron domains, 3 electron regions. And at first glance, you can look at that and say it is, I'll do it like this, molecular shape here, it's still trigonal planar. But I'll say electron, got that backwards. So really what you look at first is electron geometry. And the electron geometry here, it's 3 in a plane, it's 120 degrees. So that. This is still 3 in a plane. There's this, this, and this pair, all in a plane. So electron geometry, as in these electrons, and those electrons, the geometry they make is a trigonal plane, trigonal planar. This other one, molecular shape, now you look at it, you kind of squint your eyes and you trick your brain into not seeing this. So you're only looking at atoms now, you're ignoring the pairs of electrons. So if you ignore that pair of electrons, what are you tempted to call that shape? It's actually on that sheet. You see it? It's the one just to the right of trigonal planar. What does it say?
Bent.
Yep, bent. just the way you might want to call it, that's called the bent shape. So this is bent. So there's really kind of two shapes you notice. One, you include everything, all the electrons, including the pairs. And once you establish that, you start with that and think, okay, if I ignore this part, the pair of electrons, what do I have left? You have the bent shape. And the electron geometry decides the angle, so this is still 120 degrees. So the molecular shape of this is bent. Its electron geometry is trigonoplanar, just like this one. When you don't have pairs of electrons, the electron geometry, the molecular shape just defaults to what the original electron geometry was. So there are no pairs of electrons to ignore here, so you just go with your original assessment as trigonoplanar. You see that? And assume I'm giving you the Lewis structure to begin with. There will be some build the Lewis structure for this molecule on the test, and then when I test you on these shapes, I'll give you the Lewis structure and you go from there. You with me so far? The angles here are really obvious up here, like linear, it's 180 degrees. Trigonoplanar, three things going out into space in a plane, divide 360 by 3. I like this. So there's this, and I can take one of those off, put an electron pair on it, and you can still see that it's trigonoplanar, but ultimately it's just bent. That pair of electrons, though, see if they do. They still show it as 120 degrees. But if it's a pair of electrons, it actually kind of spreads out in space and squeezes these down. So some textbooks will go, if it's this shape, and you put a little less than sign here, and you go, it's just a little less than 120. Just because that pair of electrons squeezes the bond in just a little bit. So you have your base angle. And then if you have a pair of electrons, it squeezes in just a little. Different for different molecules. So we don't get too specific, we just say a little less than 120 degrees. All right, next on that list, next down, I'll go back to this. All right, this shape is called the tetrahedral shape. Now we've broken out into 3 dimensions. There's just no way to draw that on the board. To draw that on the board, you will sometimes see what we call dash wedge diagrams. So, what did we have? SiH4 was one of those we did before. SiH4. If you're going to draw it on a piece of paper or on a board, we draw it like that, but maybe it's obvious now that this type of diagram only shows you what's connected to what. It doesn't show you the 3-dimensional shape. If you wanted to try to do the 3-dimensional shape, we would take, how do I do this? Rotate it a little more. We would take 2 of them. If I can spin this. It's a little closer to what I want to do, but these 2, I'm trying to make those in the same plane. So let's say we did, I guess not. So I just draw the normal line for those, and then one of those, this one's coming out towards you, and this one's going behind the board. So just as a way to cheat a 3-dimensional structure, we do a dash and a solid wedge. I didn't do great with it. But you might try something like that to try to show a 3-dimensional structure. So dash wedge method. But okay, but we're to another molecular shape now. This we would call tetrahedral. And let me just do this again. SiH4 And now I'll take you through the steps. How many electron domains do you see?
4.
So now it's 4. There are no pairs of electrons. When there's 4 electron domains, the shape is tetrahedral. Or I should say, let's start over here. Now we say tetrahedral. The electron geometry, tetrahedral. This angle isn't obvious, but if you were in analytical geometry class, and they say there's a tetrahedral shape, those are all angles are equal to each other, it's 4 things coming out from a central point. What's the angle? With some math, you could figure out that it's 109.5 degrees for those. So that's kind of the only one you have to memorize. If you're following this 3-dimensional spatial stuff in your head, linear is obvious, trigonal planar is obvious. This one won't be obvious. It's really kind of the only one you have to memorize. But since there's no pairs of electrons here, the molecular shape just defaults back to tetrahedral. But now some with pairs. Got to go back to the top now. BF3, that's the BF3. It's kind of like F3. So if we did this, suspecting I did that wrong. 3 times 7 is 21, plus 3 more makes 24. 2, 4, 6, minus 6 gives us 18. Yeah. 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. I did that one wrong. So we've already covered that, trigonal planar. Frequently when you draw these and you're not trying to do 3-dimensional structure, even though this would look better, a little closer to its 3-dimensional structure by doing these at kind of an angle, it's also a legitimate way to draw it this way, because chemists aren't expecting 3-dimensional structure from this. So we frequently draw our molecules straight across and straight up and down, even if the shape would go a little better if we. So this is just like SiH4. Let me get to that. This is what I want to do. NH3. We did NH3. How many valence electrons for nitrogen?
5.
5 and 1 for each of these hydrogens. 7, 8. So we have 8 total electrons, 2, 4, 6. We're down to 2. And then there's nothing to add to the hydrogens. So you can put the last pair there. Now, how many electron domains do you see? 4. There's 4. 1, 2, 3, 4. So you're going to go, okay, 4 electron domains. It's tetrahedral for electron domain, still 109.5. But now we have one of those domains to ignore. I'm going to get off. That's what we have. It's still essentially tetrahedral. But now if you try to ignore that pair of electrons and try to come up with a shape for this, not quite. What would you be tempted to call that if you were ignoring this part? It's on that piece of paper. Trigonal pyramidal. Like the pyramids in Egypt have a square base, so there's 4. But if you see, look at this as a pyramid, this is the apex of the pyramid, and these are the lower corners. The base of the pyramid is triangular, and and it's shaped like a pyramid. Spelling wise, you have to say pyramidal, I guess. I say pyramidal a lot. They spell it that way. Trigonal pyramid, aka trigonal pyramidal. So if it's 4 electron domains and one of them is a pair of electrons, this is now trigonal pyramidal. Trigonal pyramid, triangular pyramid, trigonal pyramidal. So that's the shape of this one, trigonal pyramid. And you would still say 109.5, although truthfully that pair of electrons does squeeze that angle a little bit, so you might say a little less than 109.5. You with me? All right, one more of these, one more out to the right where it says bent. Now we have 4 things around the central point. 2 of them are pairs of electrons. Good old water does this. That's the electron dot structure of water. If I said how many electron domains, you would count 4. So you would start out by going, yep, 4. The electron geometry is tetrahedral. And then what's the molecular shape? And again, we're really asking what's the molecular shape around oxygen. But oxygen is a central atom here, so it ends up defining the whole shape of the molecule. So the shape around oxygen is now bent again. But previously when we did bent, it was trigonal planar, it was 120 degrees. This is bent at 109.5 degrees. It's still essentially tetrahedral. If I did it with this little tool. Those off. There's water. It's still tetrahedral. But you ignore those 2 pairs of electrons, you see the bent shape. And again, if I just drew a Lewis structure of water, I'm usually tempted to at least do this to make it obvious that it's bent. But the way I had it on that sheet was perfectly legitimate because, like I said, chemists aren't expecting. Both of those are perfectly legitimate ways to draw water. Chemists aren't expecting 3-dimensional structure from the flat surface, so it just shows what's connected to what and shows where the electron pairs are. All right, we've talked about 2 things around, 3 things around, and 4 things around. You might be able to guess. Next is 5 things around. All right, 5 things around. Take those off and let's just go to this. This one kind of seems complex, but you get it at just the right angle and you can see that what you really have is, wonderful shot of big these. 6. Tetrahedral. I don't want to fill around with this too much. Tetrahedral. Well, hopefully you can see it in the tetrahedral. Those are all tetrahedral. So, but you basically have, well, around what we call the equatorial position, you've got 3 atoms around that, and then you've got an atom straight up and straight down. We've got equatorial positions, and we have axial positions. And so, and we call that one, do you see the name on there? The next one down, the flag around it. What does it say?
Trigonal bipyramidal.
Trigonal bipyramidal. Can you see the 2 pyramids? One pointing down, this is the apex, and that's the base. And another one pointing up. So you have trigonal pyramidal again, but now you've got 2 of them, one pointing up, one pointing down. So that shape is called trigonal pyramidal. If you were going to try to decide angles here, hide the angles. Is it obvious that the axial positions are 180 degrees? because it's just linear straight up and down. So you've got 180 degrees there. If I turn it this way, you're just repeating the trigonal planar. So those are 120 degrees away from each other. These are 90 degrees from each other because that's just a plane right in the middle. And then that's 120 degrees. This is the only one that has more than one angle. This one has 3 different angles that you can pick out. So for that shape, PCL5 will do that. All right, so 5, and then there's one more when there's 6 things around it. Let me find one. All right, SF4. How many electron domains do you see around the sulfur? It's 5, so we're still going to do, I didn't write down. All right. So for that previous one, we would have landed on trigonal bipyramidal. And since all of them, the previous one, not this one, all of them were atoms, there were no pairs of electrons, then molecular shape was also trigonal bipyramidal. All right, this one, I'm erasing this part. So electron domain, still 5 around, so it's still trigonal bipyramidal. But if one of those 5 things is a pair of electrons, we have, we call it seesaw or seahorse. If I replace one of those, can you see it's like a seesaw? This is the base of the seesaw, and somebody would sit here and somebody would sit here, and it would go back and forth. So that one's called seesaw or seahorse. I hear seesaw more often than seahorse. So with one pair of electrons, 5 things around it, you have seesaw shape. And I'm not going to list there's 3 angles there, still 3 angles. There's a 180 degree angle. And I guess you could still say this is 120 degrees, but it would be squeezed in a little bit. These are still 90 degrees from each other. All right. I wonder if I have an example of T-shaped. There we go. 1, 2, no, that's 6. I guess I don't have an example. 6. But I'll do it here. If you have this, still 5 things around it, but 2 of them are pairs of electrons. You see why that's called T-shaped. If you try to ignore that pair of electrons, even though it's still trigonal bipyramidal, you ignore that pair of electrons, and you would say T-shaped here. T-shaped. You with me? Just a couple more. I can replace electrons one more time. You see how on the far right it says linear again? Take that out, put that in. So the 3 equatorial positions end up with the electrons in them. And you still only have 3 atoms now, but they end up 180 degrees apart from each other. So there is a specific angle here, 180 degrees. So that is, you just revert back to linear here. Trigonal bipyramidal. But then you ignore those electrons and you get, and I guess you can say 180 degrees because that's the only angle left here if you're just going to talk about the atoms. All right, that gets us down to the last one. Now we've got 6 things around. I do have some of those in here. So there's 6 things around. Start like this. you might look at that and be tempted to say, I see two pyramids again, but this time the base is square. So you might say square bipyramidal, but we don't call it that, even though that literally tracks from what trigonal bipyramidal was. We call this octahedral. Let me back up, not to confuse you, but we don't call this tetrahedral because there's four things coming out from the center. We call it tetrahedral because it's related to the tetrahedron. The tetrahedron is a shape that has four sides. So if I took a triangular plane and put it here on these, and I spun it around, put a triangular plane here, and I just did that everywhere, there would be four sides and it would be a tetrahedron. So that's actually why we call it tetrahedral, as in related to the tetrahedron. So, and maybe it helps that I explain this, but instead of square bipyramidal, we call this octahedral, because if you put planes all around it, you would have an octahedron. So that's why it's called octahedral, despite the fact that there's six things coming out. In case you're wondering why is it called hexa something, it's called octahedral because that's really referring to how many planes would complete it and turn it into a closed shape. Anyway, we have this octahedral. That's the octahedral shape. Angles, again, are obvious. This is 90 degrees here. And if I turn it like that, those are all 90 degrees. And actually, these are all equivalent. There's no equatorial or axial. They're all equivalent. So I can flip this around however I want and get a square wherever I want. So there's a square among those four. There's another square. So really, this one's just 90 degrees. I guess you could say 180 degrees, but most textbooks just mention the 90-degree angle. But it's 90 degrees all the way around. 90 degrees between these two, 90 degrees between these two. So octahedral, and this one, this is octahedral, and it's octahedral / octahedral. 90 degrees. Octahedral, there are no pairs of electrons to ignore, so molecular shape is octahedral. But you can probably see where we're going by this point. I can find one. What's 6? 1, 2, 3, there's 6. So if you look at this Lewis dot structure, 1, 2, 3, 4, 5, 6. We have 6 domains. 6 domains. But one of them is a pair of electrons. Now we get to say square pyramid. So when one of them is a pair of electrons, you see the square pyramid now? Are your eyes trained? So you got a square base, the apex is up there, and that's like the Egyptian pyramids. I had the xenon one here too. So here's 6 things around. But 2 of them are pairs of electrons. If I play the same game here, guess what? What would you call that? It's a square and a plane, so now we have square planes. Your 2 axial positions are where the pairs of electrons are, and then equatorial positions are the atoms. So square planar for that, still 90 degrees. And this sheet goes all the way out to, so we want, take that. So with the octahedral shape, you can also get a T shape if it's half and half. Half of them are atoms and half of them are pairs of electrons. T shape. You see it? And then, of course, you replace all those axial positions with electrons. You're back to linear for the very last one. You follow all that? All right. Molecular shape. And again, we're really talking about, you can look at other atoms in any of these. Like, we did this one, and I pointed here, and I said, this would be trigonal planar by electron domain, and then you ignore that pair of electrons, you would call it bent. Because it's not really linear across, it would be drawn better if it was like that. But that was for the sulfur, and since the sulfur is the central atom in this particular molecule, you can say the whole molecule has that shape. But I could point here and say, what's the shape here? 1, 2, 3. So you could say that this is trigonal planar 2. But if there's only one atom connected to it, it's necessarily going to be linear once you consider the molecular shape. I guess I don't have. All right. Electron geometry linear, molecular shape linear. And I'm really talking about the beryllium here. Electron domain, trigonal planar, and molecular shape would be still trigonal planar. This is tetrahedral / tetrahedral. This is trigonal bipyramidal / trigonal bipyramidal because it's got 5 around it. 6 around it, octahedral / octahedral. 4 around it, tetrahedral / bent. And what's the angle? Just as long as you don't say 180 degrees, because that tricks you into thinking it's 180 degrees. But it's the tetrahedral angle, the 109.5. Okay, let's look back at this. This is my copy. How many electron domains?
2.
2. So what's its electron geometry? What's the electron geometry? It's linear. The angle is 180. And then what's its molecular shape? And I'm really talking about the carbon. There's no electron pairs to ignore, so it's just linear.
So the number of bonds don't affect the shape?
No, these end up going straight towards the nitrogen, all of them, essentially. So it's still going to be linear. We're really kind of ignoring the bonds and going, here's a dotted line that connects those 2 atoms. Here's another dotted line. So we're really kind of looking at it like that. What's next? Electron pairs here. So that central atom, looking at the sulfur, double bond. How many electron domains?
3.
So its shape is no electron pairs to ignore. So it's trigonal planar, and then no electron pairs to ignore, so it's trigonal planar. All of these on the front page don't have any electron pairs. I did PF5. I did SF6 in here, but it's the same as SF5Cl, because that's still 6 things around it. Oh yeah. Get one of those, one of those, another copy of the periodic table. These I'm going to try to get to. All right, so let's see. CCl4. That one's tetrahedral, and its geometry around carbon is tetrahedral. No pairs of electrons. Phosphorus trichloride. Okay. PCl3. 20 21, 26. Yeah, okay. So you would start off by just making the backbone like that, with phosphorus in the middle. You have 21 electrons from the chlorine plus 5 more from phosphorus at 26. 2, 4, 6, 20. And then now we fill these in 2, 4, 6, 8, 10, 12, 14, 16, 18. We still got 2 left. We'll put them in the middle. All right, so there's your Lewis structure. How many electron domains? 4, and then, so the electron, this is tetrahedral, but we've got a pair of electrons to ignore. Yep. Trigonal pyramid. PCl3. CH2O. Carbon in the middle. So if we completed the Lewis structure, we would end up like that. Okay, carbon. What's the electron geometry for carbon? How many domains are around it?
3.
3, so it's
Triple.
trigonal planar. No pairs of electrons, so it's trigonal planar. Let's get to some of the larger ones. If we did CS2, we would end up with so what do you have here around the carbon?
2 electron domains.
Yep. Which makes it linear, 180 degrees.
We're just considering sulfur the same as oxygen.
Oh, yeah. Yeah, they are the same. They're in the same column. CO2 would be exactly what we're going. Some of the bigger ones. Let's see what happens. Gotta try to do it in my head. Let's do ASF5. AS in the middle. We get 35 electrons from the fluorines, and AS is 5 more, so we have a total of 40. Now we go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Oh. We have 10 left, and there they are, 2, 4, 6, 8, 10. So 5 around it. What is that?
Trigonal bipyramid.
Trigonal bipyramidal. And there's no pairs of electrons. I guess none of these. Somewhere towards the end here, we get electrons on the middle. ClF3. Cl in the middle. 4, 6. 2, 4, 6, 8, 10, 12, 14, 16, 18. 4 left, so we're going to put them in the middle. Okay, finally, one of the weird ones. How many electron domains? 5. What's the overall shape?
T-shape.
Yep,
Seesaw.
T-shape. That one's T-shape. Trigonal, bipyramidal, and then all right. SF6, we already did that. EF6, negative. When it's negative, we're going to add an extra electron. 6 times 7 is 42 from the fluorines, plus 1 from this negative. P is 5. 48. 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 22, 24. That's just going to be it. So 6 things around it. What's the shape?
Octahedral.
Octahedral, no pairs of electrons. Maybe this last page does something. CLF5. Try to do the stuff in my head. CL F5. 3, 4, 5, 6. 6 times 7 is 42. 2, 4, 6, 8, 10. It's 10, it's 32. 2, 4, 6, 8, 10, 12. This is going to have a pair. And all these pairs are here. So how many electron domains?
6.
There's 6, but one of them is a pair of electrons. Remember what that is? Yep. That one's the square pair. You guys see how this works?
Yeah.
And again, for all these examples, I'm pointing to a central atom. And really, first you say that all this stuff applies to that central atom, this stuff. But since these are all symmetrical molecules all around one atom, it ends up defining the whole molecule. So let me throw at you. So these are all kind of hand-picked because of that. But let me try. Here's a bigger molecule. So all the carbons have their 4 bonds. So So what's the molecular shape around this carbon?
Tetrahedral,
Yep, 4 things around it. How about this one?
linear,
Linear. This one?
linear,
This one?
trigonal, planar,
Yep. This one?
trigonal, planar,
Yep. And this one.
tetrahedral.
So no single one of those defines an overall shape for this molecule. It's whatever shape that makes. If you've got tetrahedral connected to linear, connected to linear, connected to trigonal planar, connected to trigonal planar. So the difference between this and all the other ones we're doing is, all the other ones we were doing has a central atom that everything radiates out from. This is what we would call kind of a linear, I shouldn't say linear for the context we're in, but so really the shape applies to the atom, not the whole molecule. It just so happens all the examples we're doing,
Okay.
the central atoms ends up defining the shape of the whole molecule. Question?
This is kind of like off topic, but I just remember learning that multiple bonds, like doubles and triples, affect the shape, like cause bends. Is that related to this? Or is that like a whole
Cause bends, no. What you're picturing is, so for this, for those two, let's say I had carbon and carbon, the molecular orbitals are kind of shaped like this. I'm hoping to get to that Tuesday, but an orbital coming with an electron, orbital with an electron, those come together to make a bonding orbital. And then the second bond here, one of the multiple bonds, it's actually doing that. And that's actually one bond. This will look confusing without a fuller discussion.
Okay, I hear you.
But this is what I'm thinking you're thinking of as bent. But those represent one of those other bonds. And then there's one more coming out in this plane and behind the board.
Okay.
Going to try to squeeze in more on electron orbitals Thursday morning. Anything else to do here? Let's look through the lab. I'm thinking y'all could do this lab without being in class, the one on molecular models. We can go through some of it though. So that first page, complete the table. Y'all can do this. Valence, number of valence electrons. Valence electrons in bonds formed. Which one are you missing?
Which one's now? This page, right?
That one.
And this one, sorry.
This is just gave you for practice.
Oh,
That's the one we just went through. This is really today's lab. What was doing? Just to remind you, we did this, and you actually did it on the test, the Lewis structure of atoms rather than molecules. Carbon, how many valence electrons?
4.
4, so you go 1, 2, 3, 4. That's the Lewis structure of carbon. How many valence electrons for hydrogen? 1, so you just go 1 and you stop. Chlorine, how many valence electrons? 7, so you go 1, 2, 3, 4. Now you start pairing them, 5, 6, 7. Lewis structure for chlorine. Oxygen, how many?
6.
1, 2, 3, 4, 5, 6. So you have 2 pairs and 2 single electrons. Sulfur, nitrogen, but the point is, the single electrons tell you that oxygen can make 2 bonds, carbon can make 4 bonds. So oxygen always has 2 bonds, and it could be a double bond going to one thing, but it's still going to be 2 bonds and no more. 2 bonds, hydrogen can make 1 bond, chlorine can make 1 bond. So that's what that first chart is. Shape, I think you can do those.
Is it asking for both the electron?
Identify the 3-dimensional molecular shape. So it says molecular shape, so it's the second one,
Sorry, I'm illiterate.
not the electron domain. For these, that's why I gave you another copy. So for number 3 on the next page, this is why I gave you another copy of this, just so you didn't have to dig for yours. It has electronegativities in the bottom right corner. So electronegativity difference. Do a couple of these. H to N. The way you do that is you look up H on here. So H is 2.1.